Hey class, welcome to our 4.1 video on forces. So we just started our new unit, which means we have moved out of how stuff moves and asking ourselves now why stuff moves in the way that it does. So in order to do that, we have to start talking about forces. So pushing, pulling, all kinds of stuff like that. But this is a big standard. So we're going to cover 4 different things. We're going to cover contact and field forces, free body diagrams, forces of gravity, and then the force of friction is all going to be encompassed in this, and we're going to get some other stuff along the way as we go. So let's go ahead and start with this idea of contact and field forces. Now, in order to even talk about that, what is a force? And that's a great question. You know, we have to define these terms. Well, a force is really any push or pull. More scientifically, it's the interaction between 2 objects. So if we have an interaction between 2 objects, we call that a force. You know that. Anytime you're touching something, you feel that kind of resistance. Put your hand on the table, you can feel that you're not able to pass through the table. So we have these 2 different types, though, that we have to talk about, because sometimes forces act and we're not touching, so we have to kind of think about it in a different way. So let's start with contact force. A contact force here is exactly, it has to be in contact. It's the force between objects that are touching. And since the objects are touching, they have to resist. Again, touch the table. As soon as you touch the table, you feel that it is pushing back against you because you can't pass through it. So that's a contact force. You're sitting in a chair probably right now. That chair is pushing back up on you, resisting that motion. The other type of force we have is called a field force. Now, field force is different. A field force acts at a distance. And the only field force we're really going to talk about in this class is gravity. Now, you could run an experiment here and jump and see if you can jump away from gravity, jump away from the earth, but you know through your own experience you will come back down to earth. Because you'll come back down to earth, you know that gravity acts even if you get away from the planet. So, gravity is the main thing. There are also the electrostatic force and the electromagnetic force that we would talk about, but we don't cover those in these courses unless we get to bonus units at the end. So that's contact and field. Am I touching, am I not, and am I being pushed or pulled? So let's go ahead and now dig into how we visualize these things. So we're going to talk about something called free body diagrams. Or shortened FBDs. And the first thing I want you to visualize is a person standing on a table. You can imagine it's me. I'm standing on the demo desk here in class. We have to think about, okay, what forces are acting on my object, on me? What's pushing or pulling this person? Well, the easy answer always is that the force of gravity is pulling down. So let's draw a downward arrow and we're going to write in the force of gravity, pulling him down. We also know from what we just learned that if I'm touching an object, it is applying a force to me. And this guy is touching the table. So the table is pushing back on him. Force of table, pushing back up on the person. Now, because of that, we now have a visual representation of what's going on. Now, we also might want to denote that, hey, he's at rest. His velocity is 0. If you stand on a table, unless the table breaks, you normally don't start falling through or jumping up in the air randomly. So it's something important to note. Now, this is just a picture. This is not a free body diagram. So to the side here, we're going to write out our rules for FBDs. Coupled with, we're going to draw the free body diagram below below it. That way we have a way to see this get put into action. So, rule number 1. Your object is a dot. Your object's a dot now. So I'm going to take my person. I'm going to represent them as a dot. Give yourself some room on the dot. Don't do like a little pinprick. Like, give yourself a good sized dot you can work with. The second rule here is that forces are arrows leaving the dot. So we always draw them leaving the dot. So I'm going to draw my 2 arrows. Perfect. Rule 3, each force is labeled with a capital F and a descriptive subscript. So what does that mean? We've had subscripts before. When we talk about initial and final velocity, we're looking at V0, VF. These ideas that there's something in there that denotes from everything else. So, force, capital F of the table. I'm going to write it really little. Force of gravity. I'm going to write it really little. And notice that it is significantly smaller. It's not just continuing the word. That way we don't get it confused with other variables or other things. It is just a subscript helping us out. Well, the last thing here is equal magnitude forces are given what are called tick marks. Tick marks. That just means, so my object here, more specifically, is not accelerating. This is the important part here, which means all of my forces have to cancel each other out. And we'll talk about why when we dig into Newton's second law. But here, I know force of the table and the force of gravity are equal because he's not accelerating. His velocity is not changing. It's 0. So they're going to be equal and opposite and cancel each other out. Same magnitude, different directions. Table would be positive, gravity would be negative. They'd add up to 0. So let's do a couple more examples here, and we're just going to draw our picture, and we're going to come back up to our rules. If you need to reference them, you have them there in your note. So example 2, we have a box being pushed at constant velocity. Now that should tip you off. Constant velocity means acceleration is 0, so we need all of our forces to cancel out in the end. So I'm going to draw a box here. We know we're going to have a velocity pointed in that direction. Here's my person pushing the box. So let's draw a free body diagram next to it here. Got my big dot, there's 1. Every arrow is a force, so I know I'm going to have gravity down, and I label it F with its subscript, F gravity. Well, it's touching the floor, F floor, and we said these are equal and opposite because I'm not accelerating. Well, I have a person pushing, so we're going to call that F push. You could say F person. But now I've run into an issue. There is one more force that exists because everything hasn't canceled each other out yet. So what could that force possibly be? Well, I'm on the floor and I'm pushing and I'm scraping against the floor. And we all know, because we've done this in middle school or elementary school, when you rub your hands together, they heat up because of friction. So going against my motion here is going to be the force of friction, because I'm rubbing up against the ground. And notice I gave it 2 tick marks. The reason for that, if they all have 1, that indicates that they all have equal magnitude, and I don't know that. But I do know that the push and the friction are equal to each other, and that floor and gravity are equal to each other, so I have to indicate that those 2 are matched up. All right, let's do a couple more here just to give us, or we have 2 more examples. We are now going to do the same box, but now I have a box accelerating. And it's going to be the same box from before, but this time, instead of velocity, I have acceleration pointed in that direction. So, what does that tell me? Well, it means that I have to have a bigger force. So, I'm going to have the same 4 forces acting here. But if I drew the same free body diagram, this would imply constant velocity, and I'm not traveling at constant velocity. So what has to change? Well, one of my forces has to be bigger, and one of them has to be smaller. So, right here, as we've labeled F table, F gravity, then my push must be larger than my friction if I'm accelerating. So if I'm accelerating to the right. Let's get a little bit more descriptive here. Now if it was accelerating to the left, which would imply slowing down, the friction would be larger than the push. Which makes sense, you know, if you're ever trying to shove something and it starts slowing on you, that's what's going on there. All right, let's do example 4 here. Last one. We have a box sliding down an inclined plane. That's just a fancy word for a ramp. Again, it's going that way. So we're going to say, we're just going to draw the forces here because we'll see that it looks different. And we'll say constant velocity. So gravity always points down. So we're going to go ahead and draw in that F gravity here. The issue becomes, though, I'm not at angles. I'm not completely X and Y 90 degree, right? I'm not square. So my surface pushes up and to the right here. So this is going to be F of my table. And friction would be going against my motion. So here would be the force of friction here. And a lot of students at this point go, well, it's moving, so it must have a force of a push going down the ramp. But that's not true. Nothing is touching this object going down the ramp. It's just sliding. What is actually happening is that we have a component of gravity here, call it FGX, that's going down the ramp. And we have a component of gravity, components going into the ramp. So that tiny bit of gravity looking down the ramp is what's accelerating it. But we do not draw these on free body diagrams. You don't draw components, you only draw the full force. Now, a couple of additional notes here for you that I want to make sure we get about free body diagrams. Number 1, velocity does not equal a force. Just because something is moving in that direction does not mean it has a force attached to it. If I throw an object in the air, so I have a ball up in the air like we've been doing projectile motion, the only force acting on it is the force of gravity. So its free body diagram would simply look like this. Even though it's moving, the only force acting on it is gravity. Second, surface force, or the, you know what I'm saying, that force that seems to be pushing up on our tables, on the ground, on the inclined plane, are always perpendicular to the surface. So if you notice, here, perpendicular, go up even farther, here, perpendicular, go up a little farther, here, perpendicular. You're starting to understand. So they're always off perpendicular to the surface. And lastly, and this is important, gravity is always down. So make those additional notes and they can help you. Now at this point, I'm going to recommend you go start the 4.1 worksheet. Go do the first 2 sections. Do contact versus contact versus field forces, and then go ahead and do the free body diagram section. When you're done with those, come on back to the video because we are going to get started on the force of gravity. So let's go ahead and talk about exactly that. Let's talk about the force of gravity. And some of you might be saying, Mr. Clark, we've already learned about the force of gravity. And I would say you've learned about something called the acceleration due to gravity. So we actually have to talk about a couple things and differentiate before we get going here. And the first thing we have to differentiate between is mass versus weight. They are two different things, and we have to talk about them. So what is mass? Well, thinking back to your chemistry class, mass is the amount of matter in an object. Now, as opposed to weight is the effect of gravity on an object's mass. So notice they're different, and we're going to use these terms a lot, and we want to make sure that we're being very specific in our language. Because if we start throwing the term mass and weight around, we're going to start getting them confused if we start interchanging them. So be very specific there. The other thing we want to talk about is little g versus the force of gravity. F sub g versus the little g that we've been talking about with free fall. So little g is the acceleration due to gravity. Everything on planet Earth has the g that is equal to 9.81 meters per second squared, or approximately 10, which is what we use on all of our worksheet problems. Now, the reason that we need to differentiate is because everything has the same acceleration due to gravity on Earth. Everything falls at 9.81 meters per second squared. However, everything does not experience the same force of gravity, which is also known as weight. So Fg is weight, and it is not the same. So force of gravity, weight, interchangeable terms. We're going to be using them a lot. That way we can understand a little bit better that this is just the force of gravity on something. Something weighs more if gravity has a larger effect on it. And because it's gravity's effect on mass, we get an equation for that. So let's go ahead and write out our equation here. Fg, or the force of gravity, is equal to mass times the acceleration due to gravity. So that's really nice for us because it's just the mass times 10 in any of our problems. It makes it really easy. But let's do some deriving here. Go ahead and try yourself. Get this into m equals and g equals form. Come back in a second. Now, if you've done it, you could find that the force of gravity, F sub g, is equal to, mass is equal to the force of gravity divided by g. And g is the force of gravity divided by m. And this is a point where we can talk about why it's important we write our variables the way that I'm showing you. Because you might think, oh look, g and g, they cancel each other out, right? It's not true. Because the force of gravity, it's a little sub g that it's a descriptor. It's not a variable. That f is the big variable that I want to worry about. So make sure you're writing these out appropriately. Now, we're only going to do one example here because this equation is honestly, it's extremely easy to use. Now I'm going to let you find my weight. So here is me again. I keep showing up. This is example 1. My mass is 76 kilograms. We know g on Earth is 10 meters per second squared. What is my weight? Well, I'll pull down my equation. It's equal to mg, which would be 76 times 10, would be 760 watts. What do I measure weight in? Or more specifically, what do I measure forces in? Because we have all these different types of forces. Well, let's do some quick unit analysis over here. So, when it comes to unit analysis, we basically look at what I'm adding up. So Fg is mass times gravity, which is kilograms times meters per second squared, which would mean that my force is kilograms times meters divided by seconds squared. And that's a lot to write. And we have an entire unit entitled forces, so I hope you're ready to write that 1,000,000 times, because scientists are not, and we're lazy. So we decided to call it a Newton, or capital N. So now you should be able to go and use this equation. You should be able to solve for different variables. It is always assumed that if we are on Earth, then G is 10. Other planets, we don't know. You can try and figure that out. Now, we have one more thing to learn about. We have to learn about the force of friction. So I would pause, go to the third section on 4.1, and then come back to finish out the notes. So let's learn about the force of friction. I'm going to try and be quick. I know this is a really long video, so thank you for sticking with me for folks who weren't in class. So there are two types of friction. Type 1 is called static friction. It is for objects that are not moving or are rolling. Rolling friction is a type of static friction. Then we have kinetic friction, and kinetic friction is objects that are sliding. Objects that are sliding. Now, I will tell you that the force of kinetic friction, KF, sorry, let's actually write that, the force of friction kinetic, because that's how it usually comes up. So the force of friction kinetic is always less than the force of friction static. The reason being, I have to overcome static friction in order to get something to start moving. It would be strange if I had something start moving, then it got stronger friction, and so I'd have to push harder, which means it would get stronger, which means I'd have to push harder, and then you would never actually be able to move anything. So we know this through experimentation. Now, why? Well, there's this thing called the coefficient of static friction. So in order to learn about it, we have to actually look at our equation. The force of friction here is less than or equal to this weird looking U called mu, mu, times Fn. And gosh, we just have, now we've, what's Fn? What does the N even stand for? I know none of this, Mr. Clark. Well, let's define this N first to get it out of the way. This is called the normal force. And it's what you learned earlier as the force of a surface. And what's convenient, and if we go all the way back up to our free body diagrams, we notice that on all of these level surfaces, so examples 1, 2, and 3, they're all equal to each other. So that's an important note we're going to make here, that if I am on a level surface, then mg is going to be equal to normal. And I apologize, it's being wonky here. So we're going to make that note that on level ground, mg is equal to the normal force, which will be really convenient for us as we work through our example problem. Now, continuing on here, what is mu? Well, this is known as the coefficient of friction. There are two. There is mu k, which is for kinetic, and there's mu s, which is for static. And as we just learned, mu s is always larger than mu k because I have to overcome static friction. So let's jump into an example problem here, and we're going to apply this equation. Now, I'm gonna decide to move a couch today. Example 1. There we go. So I'm gonna draw, my couch is now a box. And here I am attempting to push it. Now, why do we have this less than or equal than sign? Well, if I barely push something, it's going to push back exactly as much as I am pushing on it until I break static friction. So static friction is known as a smart force. So if I'm pushing on an object and it's not moving, it's going to push back with the exact same amount of force in friction to stop it from moving until I break static friction. So let's say the mass of our couch is 200 kilograms. And mu k here is going to be equal to 0.25, and mu s is equal to 0.4, which is another note we want to make. Mu is always less than 1. Always, always, always. So I want to find, number 1, find the maximum static friction. Basically, how hard do I have to push to get this thing to start moving? And then I want to find kinetic friction after it starts moving. Well, I'm going to apply my new equations, but let's first draw ourselves a little free body diagram to understand the forces that are acting on it. So, we have the force of gravity, and we have the now normal force, which we know are equal and opposite. We're going to have the force of our push, and I'm going to have the force of friction, which we don't know is equal and opposite, so we're just going to draw them in as arrows. Now, to find the force of friction static maximum, it's a lot, that's going to be our mu s times our normal force. Well, we learned down here that these two are equal, so that means the normal force is equal to mg. So I can say mu s mg is equal to 0.4 times 200 times 10, which gets me a whopping 800 newtons. So that means you have to push this couch with 800 newtons of force to get it to start moving. But then once it starts moving, I switch to kinetic friction, which now my equation looks almost the same, except my mu is now a mu k. Mu k times mg, 0.25 times 200 times 10 is equal to 500 newtons. So once you get an object moving, it becomes easier to get going. Now, funny enough, that bell is going to help indicate this is the end of the video. So you can now take what we know and go apply it on 4.1 and work your way through it. Come ask me questions in class. Come get help before or after school. And guys, as you're working through this, don't forget to be awesome.